Alright guys, so this is going to be the first of several videos that I'm going to do, first of four in fact, with regards to the kinematics equations. I'm going to show you how to work through each one. We're going to talk about how we get the information that we have. We're going to talk about which equation to use and why. And yeah, so hopefully this will be helpful as you start to look at solving other problems later on. All right, so here we go. Ashfaq is riding a bicycle in a race at 10 meters a second. He's 100 meters from the end, and in a final sprint begins to accelerate at 1.3 meters per second squared. All right, so let's go ahead and write down what we got first. Okay, we've got Ashfaq dude on his bike. Okay, I have no idea how to draw a bike. It doesn't really matter. So here's Ashfaq. He's on his bike. All right, he is 100 meters away from the finish line. Yay. Finish line done. All right. He is traveling at 10 meters a second to the right. And his acceleration is also to the right, 1.3 meters per second. So he's going to get that final sprint in to get to the end. All right, so let's write down the information that we have. And when we say what information we have, we're focused on the variables that were in the equations that we were looking at in class. All right, so the first one that I think is fairly obvious is it gives us the 10 meters per second. Now, that is how fast he's going right now. That's going to be, for our scenario, the initial. It doesn't really matter what happened before that. So this is going to be, for what we're looking at, our initial velocity. All right, now you can put the x there if you want. I'm not going to put the x down. You'll notice that anytime it has the initial velocity, it always has the vx0. Okay, the reason for the x is to remind you that everything's in the same dimension, which in this it is. I'm not going up or down or diagonally or in and out of the page. Everything will be to the right and left. All right, so I'm just going to put down initial velocity. The initial velocity is 10 meters per second. What else is it giving me? Well, he's 100 meters from the end. Now, if I care about what's happening at the end, and you'll notice both part A talks about the end of the race, and then how long will it take him to finish the race. So both of those are going to be starting at this point and ending at the finish line there. So there's two ways you can do this. The easiest way, I think, is just to identify where he is now as 0, which makes his final position 100. Again, it doesn't matter what happened before, all right? Now, if you want, you can label the final as 0, but that makes his initial position to the left, so you'd have to put negative 100. Okay, if that's difficult on your brain, then don't do that, right? Just say, well, I'm going to use the one that's going to give me a positive. To the right is positive. Remember, we've identified that here with our speed and our acceleration is that the right is positive. Okay, so we've got our initial and final displacement, which I can actually go ahead and label now. So x initial, that's the initial position, is 0 meters. And then the final position is 100 meters, all right? Now, everything here is in meters and seconds, right? Everything is in what we call our base SI units. Now, because of that, when I do my calculations, I won't really need to include the units. I'll put them in there just so you can see what happens, but it's not super necessary, all right? What else is given to us? They give us here the acceleration, right? We can see that the acceleration, again, in my formula, it's ax, but again, all of those x's is just to remind me that everything needs to be in the same dimension, which here it is. So I'm just going to put down a equals 1.3 meters per second squared, just like that. All right? Now, in the question, the other thing is, if he continues his acceleration until the end of the race, what will be his final speed, right? Now, final speed, remember in these equations over here, is this Vx, okay? Which, again, I don't need the subscript of x. It's just a label saying everything's in the same dimension. So I'm just going to put down V, which is the same thing here as Vx, All right. Now, I don't know what that is, but it's important to put that down because now I'm ready to start trying to decide which equation I need. There are 3 of them, right? But here's the information either that I have or that I want, okay? You'll notice that I have everything there except for the t, right? I don't really care about t because that is not helpful for part A. It might be helpful for part B, but I'm not worried about that right now. You'll notice that the first equation has time in it and the second equation has time in it. Neither of those really is going to help me out right now because I don't care about time. I don't have time and I don't need time. So I'm going to choose an equation that doesn't have it, which is going to be in this list, the last one. So I'm going to go, oops, that's not what I meant to do. So we're going to go final velocity squared equals the initial velocity squared plus 2 times the acceleration times x minus x naught. And that's the equation we're going to use. Again, notice that I took out all the little subscript x's because I already know everything's in the x direction. So my final velocity, which is unknown, is equal to the initial velocity, which up here was 10 meters per second, needs to be squared, plus 2 times the acceleration, which was 1.3 meters per second squared, times the final displacement x minus the initial displacement, both in meters. And there we go. So at this point, you can put in your calculator. I'm going to go ahead and work this first one through because I want to show you what happens with the units, right? So I'm going to have v squared equals, I can square that, which will be 100 meters squared per second squared, plus, I can go ahead and multiply these two, so that would be 2.6 meters per second squared. And then if I do 100 meters minus 0 meters, I get 100 meters. Now notice when I multiply those two, I'm going to have 100 meters squared per second squared equals 260 meters times meters will be, sorry, that should be plus, meters squared over second squared. So the units work. You can't add them together if they don't have the same units. These do because everything was in meters and everything was in seconds. So they have the same units. That'll equal to v squared. So I can go ahead and add those together and I get 360 meters squared per second squared. And watch, when I take the square root of the v, what I get is v equals, and I got 18.97, so I'm going to round that to 19.0, and I square root the units as well, and so what you're going to get is meters per second, just like we expect. So this is his final velocity, 19 meters per second. Jamming, right? Okay, so we answer the first question. That's his final speed, 19 meters per second. All right? The second question is, how long will it take him to finish the race? Okay, so now I'm looking at time. Recognize that I'm still starting at the same position, same initial velocity, same acceleration, same final position. Everything's the same. I also now have the final velocity, which is 19.0 meters per second. And so now I'm going to go over and I'm going to choose an appropriate equation. This time, I don't want the last equation because it doesn't have time in it. And time is actually the thing I want now. And so I'm going to choose one of the other two equations. It doesn't matter which one. It's up to you. You can choose which one you want to do. I'm going to choose the first one. The reason being is because it looks easier, right? It doesn't have any squares. It only has one t. So I'm not going to do that second one. I'm going to go with the first equation here. So that's the final velocity is equal to the initial velocity plus a t. And those numbers I have. So the final velocity was 19.0. The initial velocity was 10 plus the acceleration 1.3 times time. And at this point, I trust that you can plug that in and work it out. And when you work it out, you should get that time equals the last one I did in 3 sig figs, so I'll do this one as well, 6.92 seconds. And there's our time, that's how long it took him to finish. And you'll say, but yeah, it was 10 meters per second and 100 meters. Shouldn't it be 10? No, he was changing speed. Remember, he was getting faster and faster and faster, so it should be less than 10 seconds. This answer makes sense in the context that we have, which is awesome. That's what we want. Everything should make sense. It should be predictable. It should reason out. Okay? Now, the one thing I will say is that in the question, everything that they gave us, and we're gonna start looking at our idea of significant figures here. Everything here, really, this only has one significant figure, right? Because it's 10, we don't know if the 0 has been rounded or not. The 1 is the only significant figure there. The 100 meters, that's one significant figure there, right? So really, I only have one significant figure. So both of my answers, technically, this one, yes, this is two significant figures, but we always do the smallest. So technically, my answer should be to only one significant figure. That means that my velocity will end up being 20 meters per second, because I'm going to round to the first significant figure. And then my time is going to be 7 seconds. I'm not going to put a 0.0 or anything because I only want it to be one significant figure. All right, so that's the answer, and that hopefully gives you an introduction to using these kinematics equations. Go ahead and watch the next one.